So this first example of simplifying a radical expression is going to be a rather quick one, but it really lays a foundation for how we're going to simplify more intricate radical expressions later on. So in this problem, we're just given the square root of 45 and asked to simplify it to the extent that we can. So what does that mean? What's our strategy going to be? Well, we can quickly convince ourselves that 45 is not, in fact, a perfect square. We could run through the whole numbers between, let's say, 1 and 10, and if we multiply each of them by themselves, none of them are going to give us 45 when we multiply them by themselves. In fact, we can say for sure that the square root of 45 has to be between 6 and 7, because 6 squared is 36, which is smaller than 45. 7 squared is 49, which is bigger than 45. But that's as much as we can say. It's not a whole number, so this answer is not going to be a whole number either. Instead, what we can do to simplify this expression is to look at the number 45 and break it apart into its pieces, break it apart into its factors. What is 45 comprised of? And if any of 45's factors happen themselves to be perfect squares, then those perfect square factors can be pulled out from under the radical. So to simplify this radical expression, we're just going to do that as much as we can. So step one is going to be to factor the radicand completely, factor the number 45 all the way into primes. Then we're going to look through those prime factors and find out if there are any that are repeated. If there's a pair of factors on the inside of a square root, that's equivalent to a single one of those factors on the outside of the square root. So that's going to be our guiding principle for simplifying square roots, is that a pair on the inside is worth 1 on the outside. And once we've done that step as much as we can, we'll remultiply any factors that remain to simplify our answer. So let's talk about the number 45. What's it made of in a multiplicative sense? Well, to figure out that answer, we're just going to factor the number 45 as much as we can. The usual technique for doing this is making a factor tree. So 45 has 3 as a prime factor. It's 3 times 15. Then 15 also has 3 as a prime factor. It's 3 times 5. And then we've completely factored 45 because all the numbers at the end of these branches are all themselves prime, 3, 3, and 5. So 45 is really 3 times 3 times 5, and that's broken apart as completely as possible. So we'll just replace 45 underneath that radical with 3 times 3 times 5. Now we've got it completely factored. We can start looking for pairs, because a pair underneath the square root is worth 1 on the outside. And here we happen to have one pair. Specifically, the pair on the inside of our square root is 3 times 3. And the reason that this works, by the way, is that square roots break apart across multiplication and division. The square root of a product is the product of the square roots. The square root of a quotient is the quotient of the square roots. And because of that, the square root of 3 times 3 times 5 is the same thing as the square root of 3 times 3 times the square root of 5. In other words, we can take the square roots individually of all the factors underneath the square root. But the square root of 3 times 3 cancels. Right? The square root is asking the question, what number multiplied by itself gives us the answer 3 times 3? Well, that's a question that answers itself. 3 is the number which, when multiplied by itself, gives you 3 times 3. So the square root of 3 times 3 is just 3. That's the point of this exercise, and that's why this technique works. So that pair of 3's underneath the radical became a single 3 on the outside, because the pair turned into a 9, and the square root of 9 is equal to 3. But that 5 is left over. There's nothing we can do with that 5 underneath the radical. And so that 5 underneath the radical is also part of our final answer. So when I simplify the square root of 45, I'm going to get the square root of 3 times 3 times 5. But the square root of 3 times 3 turns into a single factor of the whole number 3 on the outside, while the 5 underneath the radical doesn't have any other 5 to combine with to make it any simpler. So it's stuck there. So the square root of 45 simplifies to 3 times radical 5. If there were any more simplifying to do, we would do it here, but there's nothing else that we can accomplish. Let me just do one more quick example where there would be some more simplifying to do at the end of the process, just to make sure we illustrate all the steps that could possibly happen. Let's think about the square root of 360. Using the same technique, let's figure out what are the factors of 360. What does 360 break apart into? Well, it's 10 times 36, and 10 is 2 times 5. And 36 is 6 times 6, and each of those 6's is 2 times 3. So if we factor 360, we find that it has 6 different prime factors. 2 times 2 times 2 times 3 times 3 times 5. So we'll just replace the 360 underneath that radical with its factorization into primes. Now we're going to go looking for pairs. Every pair on the inside gives us 1 on the outside. And we can start by taking a pair of 2's from underneath the radical and bringing it outside to make us a single 2. But then we also have a pair of 3's underneath the radical that we can bring out and make a single 3 on the outside. If I pull both of those pairs out of the radical, I'm still going to have a 2 and a 5 underneath, but I'm also going to have now a single 2 and a single 3 on the outside. So in total, I'm going to have 2 times 3 that come out as whole numbers, and underneath the radical, I'm going to have 2 times 5. Now is when we would do the additional step of simplifying to re-multiply back out the factors that we had. On the outside, 2 times 3 gives us a 6. And on the inside, underneath the radical, 2 times 5 gives us a 10. So to factor the number 360 using this technique, we would first factor 360 completely to figure out what pairs can then be brought out. And we found a pair of 2's and a pair of 3's, which when we bring them outside the radical become a single 2 multiplied by a single 3. That gave us the 6, the whole number 6 that we got on the outside of the radical. Then underneath the radical, we still had a 2 and a 5 left that didn't pair off and become simpler, and so those remultiply together to give us 10.